Okay, so the recording is now active. Please note that your presentations are being recorded and will be hosted on YouTube, right? So bear that in mind. Okay, yeah. So when we are ready, presentation should be 8 minutes with a couple of minutes for questions.
Okay, I guess I'll just do it like this.
You can start a slideshow if you want.
Oh, do you see it?
Yeah.
Oh, okay. I wasn't sure. Okay. So our project is counter training for object detectors. And these are our names again. So I'm just going to start with going over our technical approach. And I think it's more useful to look at the diagram here. And we've seen it before, so I'm not going to spend too much time on it. But pretty much we're starting with the YOLO object detection model, which is pre-trained on the COCO dataset of a bunch of common objects. We're doing transfer learning with some data, a small amount of labeled data from the MyoTCD dataset. And then overall, we've always been looking at doing then some counter training, or more precisely error-driven learning on YOLO. But we wanted to try to eliminate the reliance on so much labeled data in that process. So after the literature review, we introduced this prototype neural network, which we'll work on that in future weeks. That'll rely on ResNet, which is pre-trained on the ImageNet dataset. And then we'll use a small amount of data from MyoTCD to form prototype clusters in the prototype network. And then we'll check YOLO's predictions on unlabeled data with the prototype network. And if they disagree, we'll judge that as a false positive and use that. But in these first couple of weeks, we've been focusing mostly on the YOLO half of things, setting stuff up for the training with counter examples from there.
Okay. I'll take over the screen share from you, Max.
Oh, okay.
Can you guys see that?
Yes, that's good.
Okay, so regarding the current status, we have done the data preparation, which means we dump the MOTTCD datasets. It's about 100K images, and we converted that to a YOLO 1.1 format. This could be accepted for retraining YOLO. And then we split datasets into 3 sets. There are text, training, and counterexample at the ratios of 10, 1, 9. And the training set is used for fine-tuning the model initiated with the COCO pre-trained weights. And the text set is for just for testing the, for example, precision record, average mean precisions, those metrics. That could stand for our overall performance, because the test set takes half of this data sets, which means about 50K. So it should stand for the overall performance. And the counterexample is just for, we suppose those portion of data, it's not, it's unlabeled, but it's actually labeled. We use the label to automatic gathering some false positions annotations. And those are for the error-driven learning. So what we have done, basically what we do is, what we have done is we train the YOLO, we fine-tune the YOLO to do the domain adaptation from the COCO domain to the MOTTCD domain, use only 1/20 of the data sets. And then we kind of use the way to do inference on the 9/20 of the counterexamples. And because we have the ground truth annotations of those portions of data, then we can automatically generate the false predictions annotation. And then we're gonna do the error-driven learning, use that false prediction annotations. here's how we modify the model. As you can see, how can I go back to the?
You can use the arrow keys, or you could, yeah.
Yeah, I clicked by mistake. So still looking at the modification to the model, we need to modify the loss function as we mentioned before. And on the left-hand side, that's the original YOLO loss function. The first two terms describe the bounding box loss, which means if the coordinates, there are so many background knowledge before understanding those loss function, but in the high level idea, this will this loss, this two term will give us smaller number as the bounding box get close to the ground truth bounding box. And this one is describing the confidence of the bounding box prediction. The higher, so the ground truth will be just one. If they're in the ground truth bounding box area, then the ground truth will be just one. The CI hat will be just one, and and here's the prediction. And the last term is, I think these two terms are responsible for the confidence. This one is if they're in the bounding box area, then this one will be 1. Otherwise, it will be 0 in this. And then the last term describing the classification loss, and just say a mean square loss. But we changed that to another loss function. In the first term here, this very long term here, we kind of need to modify that. If that is a false prediction, a false localization, then we want the bounding box to not overlap with the ground with what is annotated, and that loss function term describe that. And the second term used to describe the confidence. And since in terms of the false localization, the ground truth is just 0 instead of 1 in the original loss function, then we just use 0 minus CI square, then which is CI squares. And then the last term describe the misclassification. Here are two. We also use some trick to implement this loss function. Any questions so far, Professor? Did I make myself clear?
Yeah, thank you. So in general, I probably won't be asking questions during these presentations, right? What I'm doing is I'm taking notes, and y'all will see all of my comments on Canvas.
Okay, yeah. And yeah, I asked because I don't think this one is ideal, and we still need to improve that. I'll talk about the challenge we have encountered so far in the next few seconds.
Okay.
Regarding current status, we implemented the loss functions, which can fuse false localizations and misclassification together. And then we fine-tune the pre-trained weights for 15 epochs. Then this way were used to gather the false prediction annotations, and the false prediction annotations are used to conduct error-driven learning and for 1 epochs. And here's some result we got. And on the left-hand side, that's the 50 epochs of training, because it initiated with the 10 epochs of training. So I just attached the second, the 40 epochs of the. I just attached the last 40 epochs of the curve, and using this way we gather about 5K false prediction annotations from the counterexample datasets, and we use the false prediction annotations to do error-driven learning on initiate with this way, and then we gather 266 false positive localizations and 0 misclassification. And here is the matrix. You can see now we suffer from the low records, which means not much bounding box were detected, because there are half forced localization and about half misclassification. The ideal record should be about 50%, but now it's far from there. So, which means to me, the loss function we decided does harm the records. It will lead the model to make less predictions, then it will make less mistake intuitively. And here is some quantitative results, and those are the false positions that we gather. And here is one. It bound the heads of the car as a car, but actually it's not true. And on this one is more clear. It bounds nothing as something. So this one should be definitely a false localization, and we're gonna use those bounding box to retrain it. That's just a visualization of the false position annotations. And also those has the specific class name on top of those bounding box will be just a misclassification. And here is the error-driven learning results. On the upper images are the fine-tuned weights, and this one is after the error-driven learning. You can see that it makes less predictions, just to make less mistakes. And so the current challenges we are facing are, firstly, I think the MOTTC annotations are not fully annotated. There are many small objects are not annotated, but it could be detected as it can be detected as objects of interest using the way we fine-tuned. So those ones are not actually false localization, but because they were not annotated in the ground truth labels. So we detect them as false localization, and those ones are also used to retrain the model. So I think that's also another factor for harming the record. And yeah, also the record was harmed too much. We got some idea to fix that. First, we can think about fusing the regular training with the error-driven learning, because if we have the regular annotations, it may prevent the model to get less recall. Because
thanks a lot. Yeah, we are out of time, so I'll have to stop you right there.
Okay.
So can I ask, since there won't be any time for questions, so can the group 2 door differentiation please set up? So please share your screen. Yeah, so in general, a great presentation, team. So yeah, please watch out for my comments on Canvas, right? And yeah, take the time to respond to those comments in your next update. Okay, great presentation in general, and appreciated the quantitative and qualitative results, as well as the enumeration of challenges. So that's great presentation.
Okay, thank you, Professor.
Yeah, okay.
Yeah, there's more to the presentation, but y'all can just look at it.
Yeah, will do.
Yeah.
Thank you. Okay, so yeah, so team 2, are you there? Door differentiation?
Yeah, I couldn't share until the other group stopped sharing. So I'll start sharing now.
Yeah, get started, and please monitor the chat. I don't want to disturb you all, so monitor the chat. I'm putting timing constraints there.
I'm not sure that we can really see the chat while we're sharing a screen.
I'll like be looking at it, so I'll let you know if there's any.
Okay, yeah, so you can just say aloud if we're getting low on time. So should we start now?
Please, good.
Okay, so this is the door differentiation group. To give you a quick little refresher on what our project is about, we're essentially trying to create a model that can take some kind of image or video input of a door, and then we'll determine what kind of door is in that picture. So that'd be things like elevator door, door with handle, and things like that. So we plan to phrase this as like an object detection problem as opposed to something like, say, image classification. So to do this, we're going to build on top of the YOLO v5 model, which is this pre-trained object detection model. YOLO v5 is good at kind of detecting more like general objects, but doesn't have much in it for doors. So to get it to work for our problem, we're going to need to create a custom data set YOLO v5, the image that takes can be kind of particular in terms of format and what kind of labels we need. So we need to gather all of that. Once we have all that data, we can train YOLO v5 on this additional data, which should specialize it for our problem. We want to create two types of models. The first one is, as I said before, the door differentiation model, but we also kind of want to create these supplementary models to look for secondary features. For example, if you find a door with a handle, then we want a model that can actually find where that handle is. I think I forgot to mention before, the door differentiation model is primarily meant to be used by visually impaired people. So it's important to be able to find these other features like handles, knobs, buttons, so we can actually tell the user where these objects are. As for our current status, we're working on assembling this custom data set. So to do this, we first decided on exactly what kind of doors we're trying to find. I have them listed all here in the first bullet point, everything from elevators to revolving doors. So to do this, we're gathering a few hundred images of each types of doors, reformatting them all to the format that YOLO v5 needs, which is things like JPEGs. They have to be kind of square format in terms of pixel size. And then we have to actually do these labels. So on the right in this image, you can see this is one of the images from our data set. So for each of these doors in the image, we have to create a bounding box around it with the proper label. And you can see some of the images have multiple doors in them, and they can also have multiple different types of doors. So it kind of is just tedious to go through and do this when we're working with so many images. We basically have to do these one by one. We did look at some pre-existing data sets before making our custom one, I should mention. And although some of them had doors in them, the labels for them didn't really differentiate between these different types of doors in the way we wanted. So we ultimately had to go through with just kind of making our custom data set. So as I said before, we were only really getting like a few hundred images of each type of doors, which isn't really enough probably for a solid object detection model. So we asked our mentor about this, and he suggested doing some data augmentation. So that would involve kind of putting some like transforms on these images, doing things like say just like zooming in and out to rescale it, flipping them around or rotating them. This kind of slightly alters the features in the image, so it'll make your model more robust, and we can greatly increase the amount of training data we have without actually finding completely new images. Another approach he offered was kind of creating this like synthetic 3D environment in something like Unity or Unreal Engine, where we have these simulated doors, and then we could take pictures of those. But we're probably planning to go forward with data augmentation rather than that approach. After that, we want to go forward with actually building on top of YOLO v5, because at that point we'll have our fully completed data set. And then we of course want to do some testing on that to make sure it's actually working as intended. And then after that, we want to work on deploying the model. So that would involve creating some kind of application running on like a phone or some standalone machine like a Raspberry Pi, which is going to take camera input, pass it to our like door detection and door differentiation models, and then output it with some kind of like text to speech.
Okay, so I'll pick up from here. So our current main challenge is really thinking about the best way to scale up our data. So as Ken mentioned, we are sort of leaning toward shifting and changing the images, but we thought it was important to maybe go through the pros and cons of how we came to that decision. So the first way that we talked about is sort of shifting the images. So this could be rotating, it could be flipping left and right, up and down, it could be blurring the images. The sort of con with this is that we would have to do this one by one. It would be incredibly tedious and incredibly time consuming. And then on top of that, we would have to go through and do the bounding on each of these images again. The other option that we had was creating a 3D synthetic environment, which Ken mentioned as well. This would be incredibly work intensive for us to create, but there are advantages to doing this. A lot of these applications that allow you to create this 3D environment would make it easier with the bounding because of the way that these images are already created. That said, we are sort of leaning towards shifting the images. We think it would probably be more intuitive for us. And that way our model is working only with sort of the quote unquote real life data that you would encounter out in the wild if this were to become a real application. Ken, can you go to the next slide?
Yeah.
So this is our timeline for the remaining goals. We've sort of set up a Gantt chart with, sort of daily, how we can do, track it through the days. So we don't really have many hard deadlines other than the hard deadlines that were set by the professor, but we do have sort of time estimates for how long we think things will take. So our goal is to have our full complete data set finished by the end of this week, and then to spend the next week or so after that trying to work on the data augmentation. As we said, it seems to be quite time intensive. So we are trying to budget a little bit extra time to do that because it is a really important part of building out our model. And then, as Ken mentioned as well, we are planning to work on 2 separate models that do different things, even though the hope is that they will be able to work together going down the line. So the first is the door differentiation model. The second is to be able to identify doorknobs and door handles. The plan is to work on those 2 things concurrently and then sort of bring them together at the end. Can you go to the next slide? And then just to reiterate, our end of semester deliverable is 2 separate models, one that's able to detect different types of doors, one that's able to detect different types of doorknobs and door handles. Our nice to have is integration with either a phone application, a Raspberry Pi, something that allows our model to be usable in a functional way. And so that someone who is visually impaired would actually be able to use it. And that's it, I think.
Yeah, it should be everything. Any questions?
Great, thanks. Yeah, so maybe stop sharing, and I would ask group 3 to begin sharing. And while they do that, is there a quick question? Any questions? Okay, no questions. Group 3, embodied conversation agents. Can you please share your screen?
Hi, can you see this? Can you
Yeah,
hear me?
wonderful. Yes.
Okay.
Sorry, just back to group 2. Yeah, in general, great presentation, and yes, I do have several comments for you. So yeah, please watch out for that. All right, group 3, get started.
All right. So, hi, we're group 3 for embodied conversational agents. Our presentation will consist of 3 different subtopics within embodied conversational agents, each subtopic being discussed by different people. So I'll begin first on my topic, which is affect-driven dialogue. So just like a brief introduction before I just go, and along with the current status. So the goal of using with affect-driven dialogue is to utilize ECAs to manage. Yes.
Yeah, sorry. So okay, so y'all are giving 3 sub presentations, right?
Yes.
Okay, so I will time you all to about 3 to 4 minutes per individual presentation. Okay.
Okay, sounds good.
All right, thanks.
All right, so the goal essentially of this project is to utilize ECAs to manage dialogue and to be able to associate different emotions based on different input for dialogue and to associate those inputs. And it uses embodied conversational generation systems. You can create tasks and like capture the emotion changes. I'll show an example of this in the next slide, like just to capture emotions and be able to assimilate them based on just different inputs. And based on what, after being able to do that, I will next would involve doing something called curriculum dual learning, which would be just using dual tasks within the conversation generation to associate multiple emotions for each response. Since for each response, there's typically more than one emotion that can be associated at a time. So my current status is I've identified emotion classifiers and data sets to test the dialogues with ECM. So the emotion classifier I'll be using is one from Google called GoEmotion, which is 28 different emotion classifications. And the data set I'll be using initially is the Cornell Movie Corpora dataset, which has over, I want to say, yeah, it has 58K different text, different sentences in text that I will be using as data sets to log emotion. So just some expected results from tests. These are just the expected results from an emotion conversation generalization. So with the corpus that I mentioned earlier as the data set, I would be able to classify them into different emotional responses. So based on each different text that appears or different sentences, I'd be able to categorize them using an ECM to different dialogue. So for like a certain post, I would be able to categorize them accordingly, like in the bottom left corner, bottom right corner. And based on that, some of the expected results. So the current ECM that's being used, that was being tested right now, is one that uses a Chinese data set. So I would be changing that one as well to be using an English data set along with a significant more text and using more different associations for emotion. So just as an example of like the different responses that are being shown within here for this. So, and the reason I show expected results is just some of the current challenges I'm having. I was testing it earlier and I came into some issues with it just with using different languages that I'm not super familiar with. And basically just running it itself, it was taking a significant amount of time, which I would be ironing out this week. But just some general challenges with effect-driven dialogue, or just the fact that emotion factor and quality generation of emotions is typically weak due to just the data sets being used. There's a lot of variance and ambiguity for
Surya, can you conclude? I'll have to stop you.
Oh, sure. And yeah, just current data sets do not account for empathy. So the planned next steps are to continue working on ECM and Cornell movie corporate data sets, and to apply the curriculum dual learning for like multi-emotional labeling using those. So as I just mentioned, the timeline would be very similar to what I just described with using Go Emotion and the Cornell data set to incorporate all of this and to enable.
That's fine, thanks. Anything else?
All right. And yeah, the expected delivery will be a report of all of my findings and just a demonstration of showing how the assimilation occurs. That's it.
Okay, great. All right, so maybe the next student can get started. And okay, oh, perfect. Is there a quick question for Surya? Okay, if there's no question, go ahead, Abdullah.
All right. So I'm also working on the ECA project with Surya. My role is more on creating emotionally aware gestures. Next slide. Thanks. So this is the main project that I've been working with. And essentially what this project does is, given raw speech input, corresponding text transcript, a speaker ID, and seed poses, it will create a emotionally aware gestures, which you can see on the bottom right over there. Next slide. All right, so video loaded, that's good. So for the technical approach, my first step is going to be to effectively reproduce a speech to affective gestures project, which I was able to do. If the video over there works, you can hit play. It might not. It's okay, but yeah. Yes, this is an example of what I was able to reproduce last week. So I had to modify the project a little bit to, make it appear that way and really make it in a more understandable way for myself, so I can edit it and work with it later in the future. Next slide. All right. So I also need to. So my main goal is going to be to, instead of making the gestures correspond to some seed pose and speaker ID, I want to use some combination of speaker ID and seed poses and assign that to some emotion. So what I'm working on now is I'm going to create around 50 simulations of emotional gestures, which is some combination of the speaker ID and seed poses. And then based on my personal opinion, I'm going to assign an emotion to 20 of them that I believe carry the most emotion, right? From there, I'm going to create a statistical study to kind of evaluate the accuracy of my personal opinions, which are, of course, not valid, my intuition. Next slide. So this is a overview of the statistical study itself, how I'm going to go about determining the validity of these 20 or 25 combinations of the emotions. So once I'm able to do all of that, I have a program that, given an emotion and given audio and text, it can create a emotionally aware gestures generations. Next. All right, so some of the challenges I've been working with, the project, the speech to affective gestures project, is very extensive. It's a lot of code to work with. So kind of understanding exactly what their methodology and their low-level format has proven to be relatively difficult. I've been working with the iLab and SSH. There's been a little bit of technical difficulties on that behalf. And then also I need to create a very low bias statistical study to determine how accurate my findings will be. Next. All right, so these are the next steps looking forward. So I'm going to create the gesture generation simulations this week, and then I want to have my statistical study kind of drafted, and I'll put it out, and I'll definitely send it to the Discord and wherever other resources I can find, and then I'll write some conclusions. If it's inaccurate, I would of course repeat it. I'd modify the project so I can manually input text and speech. And then hopefully if I have time at the end, I'm going to incorporate Google Cloud text-to-speech, which I've already implemented on my computer, but kind of incorporate it with this project. So I can only have text as input, and then speech would be created from that, which would then be the project stuff. And there's my final deliverable, which would be a combination of all of these steps.
All right, thanks a lot. All right, let's move on to the next presentation. Yep. Go ahead, Rajat.
Yeah, hello. So yeah, I'm also doing this as part of the ECA project, and I'm working on facial reconstruction and rendering, specifically improving upon the current methods. So you can go to the next slide. Yeah, so right now, like current 3D facial reconstruction methods like pose problems like poor generalization and lack of facial details that give it realism, and also have a lack of temporal coherence. So what I propose is a multi-stage adversarial training of the reconstruction and rendering networks, leveraging like encoders, neural networks, etc. from the current state-of-the-art techniques. So here's just a technical overview like of what I'm trying to do. So there are like three main SOTAs here. That's Deca, rendering with style, and Nerface. So what I'm trying to do is to use the latent codes from say Deca and try to input that as the parameters for the neural renderer, and possibly even the other way around where I can combine the complete latent code with the Nerface renderer. Yeah, you can go to the next slide. Yeah, this is just an overview of how I'd like to split the course and detail maps and potentially combine the course shape finally into the neural renderer and add the other facial details like say hair or inner jaw in the end after we get the detail map. Next slide. Yeah, so this is actually one of the first things that I try to implement and modify upon. So Flame is faces learned with an articulated model and expressions. So this is one of the SOTA methods for getting a course shape. So this is these are results with just like 10 parameters being edited, but there's over 100 parameters. You next slide. Yeah, so this is an important geometric prior for the facial reconstruction because these give the parameter for things like facial identity, pose, expressions, etc. So there are over like 5,000 vertices over which the blending is being done to create this structure. Next slide. But unfortunately, a flame doesn't have a appearance model, which is important as a input for the neural renderers. So I'll have to use the basal face model for the linear albedo subspace, which has to be given. So I'll have to convert the BFM subspace into a flame UV layout to make it compatible with flame. So yeah, that's the output UV albedo map. Next slide. Yeah, so once I extract the appearance model also, then I can use any traditional pre-tracing software to get the skin. And once the skin is outputted, then use any like neural renderer like StyleGAN to which is already pre-trained on datasets to create the rest of the full portrait image of the face. Next slide. So the current status is I'm working on the MEAD dataset, which is a very large dataset, and I've already pre-processed for the DECA training, which is basically just getting the 2D landmarks and segmentation model, which is just for like one pose, and also reproduce DECA and nerve phrase results. Next slide. So this is the results from DECA. So as you can see, I think the first 3D model is from the normal flame model. You can see it's not that detailed, but once the displacement map is added on, you can see more facial details added on the 3D map. But if you look at the second last column, you can see that the texture mapping is really bad. So I can't really use this for the real-time 3D facial creation because it doesn't really account for the skin features, and you can see the inner mouth and everything is missing. So these are just like filled in. There's nothing in it actually. So next slide. This is just you can play the video. Yeah, so this is just the output from Nerface, but Nerface uses a different approach to rendering. So Nerface implicitly represents the head based on a scene representation network. So to handle the dynamics, like they combine a low dimensional morphable model, which provides explicit control over pose and expression. So this, even though it looks pretty good, like this is a non-real time. It's done through many images and just combined. So potentially could use a better low-level model like Flame to get better temporal coherence. Next slide. Yeah, so there are a lot of challenges. So the first obvious challenge is how to get the a priori for the neural network from the DECA model, since the appearance model is missing. So that's one thing I'm trying to figure out. I mean, that's the main blocker for me right now. The rest of it is pretty much implementation of current methods. Next slide. Yeah, so the planned next steps are to train the DECA on MEAT dataset that was created, and then mapping the core structure for the intermediate facial features, and then extracting the ray traced skin from that. And then finally, to use the neural render that we saw to potentially in-paint the rest of the eyes, hair, and inner mouth regions. Next step. And this is just the same thing.
Yeah, so okay, Rajat, yeah, I'll stop you right there. Great, yeah, time's up. So yeah, great presentation, team in general. So please stop sharing. And can I ask group 4 GeoPixels to share the screen? And what? Yeah, are you there, GeoPixels? Yeah, okay. Yeah, and then just so I think Catherine had a quick question, right? Is how will these 3 projects be combined? So that's a great question, Catherine, and it's actually something that maybe I should answer. So so this team is working as part of a much larger initiative in our group, right? Which is being led by one of my PhD students. So yeah, so I think they are definitely not responsible, right, for the integration. But hopefully everyone can see, right, how the work in gesture animation and facial animation and emotion classification can contribute to the development of a much larger integrated embodied conversational agent framework, right? And that's what this team is working towards. Okay, so GeoPixels, your time starts now.
Hello, everyone. My objective of my project, the objective of my project was to develop a framework for semi-automatic monoplotting using monocular image and DEM. So our algorithm is like this, has 2 parallel parts for finding and detecting and finding image key point and DEM key point. So we can represent DEM as a point cloud and a raster image. We can use raster image and implementing a key point detector on it to find its ground control points or key points, and then use an affine geotransform method to find the XYZ of a world coordinate system of the DEM key points in meter dimension, and then we can have initial guess for camera parameters, and using those initial values, we can implement perspective projection of DEM key points, and then compare those projected points with the image key points, and if they are matched, so we are done with the optimization, and if not, we can update the camera parameters by gradient descent optimization. So after the optimization is done, we can implement ray tracing for finding the visible and invisible points, and then establish a correspondence between DEM between each pixel and DEM points which are in the world coordinate system. So in the first step, we implemented different methods for image key point detection. I used Shitomasi, SURF, SIFT, and ORB for finding the image key points. Among them, among the different experimentation, ORB was the better method. And also for the image key point detection, I used a pre-trained key point detector model, which is called SuperPoint. I also tested this model on several images, but the challenge was that this model detects extra points, although it was very good for detecting the required features, for example, the peaks of mountains. And in the next step, for DEM key point detection, I tested different methods, and again, ORB was the best among the different tests. And here are some results for the DEM key points. For one of the steps in the algorithm, we need to have DEM mesh surface, and I use a triangulation method to generate a DEM mesh surface as shown in this slide. For the matching optimization step, I implemented for a synthetic case to make sure everything works well. For the loss function, I considered distance between projected points with nearest image key point in the image plane space, and then I implemented all the projection equation in PyTorch as differentiable functions that we can use them in gradient descent optimization. I should say that the method is robust to mismatch between key point numbers in DEM and image. For example, in this figure, you can see that the number of image key points is less than the number of DEM key points, because some image key point detectors may not be able to detect all the key point of our interest. And then for matching optimization, I implemented for a real case. In this case, ORB key point detector was used, and I had a challenge for the existence of extra key points that the detectors found. I had to manually choose some of the important key points in both image and DEM. I had some challenges, and I developed some ideas to improve the method. One of the challenges was the dependence of initial guess value for the optimization. For some initial values, the optimization process was not converging. My idea was to consider a smarter selection of initial conditions. For example, I represent my idea in this figure that we can have several candidates of initial camera position such that from that location, the camera can view all the points such that no projected points are located over each other in the same place. And another challenge was the low speed of low speed convergence. The idea was to use a regularization term in loss function, regularizing based on the distance of average or mid point of image key points and average point of projected points. And here's the equation for regularized optimization. And the other challenge was getting stuck in local minima in the optimization process. For example, in this figure, you can see that all the projected points locating near each other and also near image key point. The idea was to add a regularization term to the loss function, considering that the average distance between projected points should not be around 0.
About 1 more minute, so please wrap up. Thanks.
Okay, sure. I use a regularization function, which its gradient is very large near low values and small gradient in large distance values. So my plans for next step is to complete the whole process regardless of the challenges, and also use the results of matching optimization for monoplotting by implementing a ray tracing algorithm to detect hidden projected points and find the world XYZ coordinates of pixels, and also develop an algorithm to solve the challenges of extra image and DM key points. And I should also note that unlike our method, all the reviewed study in the literature considered some prior information for camera localization. So in case the project is too much challenging, I can start a new project topic with the permission of Professor Kapadia. And the new idea is on floodwater segmentation and manual monoplotting for mapping flood images. Yeah, thank you.
Okay, thanks a lot. Okay, so please stop sharing. Group 5, graph sketch query, please share screen. Yeah, Behzad, I think we already discussed, right, about you potentially switching projects, right? So as I said, I mean, I give you 2 options so you can decide what you want to do. Okay, yeah, but overall, great presentation, and I appreciate the discussion of challenges. All right.
Thank you.
So please, group 5, please get started.
Yes, I'm Hao Yangzhang, and my project is graph sketch query. So just to recall what it is, I will give the formal definition. So the input of the problem will be a sketch image, which describes a query graph. And the sketch image contains a collection of 2D coordinates of the points on the sketch and the connected adjacent points between those coordinates on each stroke. And the user will be allowed to do 3 things. First is to draw a circle to indicate a meta node. And they can draw lines between circles to indicate the meta links. And they can write down symbols like F4 and K16 inside the circle to indicate the label of those nodes. The output of this problem should be a subset of graphs such that they are similar to the query graph. The similar here means that the distance between the answer graphs and the query graph is minimized while maximizing the distance between any two graphs. So here is the flowchart of my approach. So the input will be a sketch graph, and we first do this sketch segmentation to segment it into node sketches, link sketches, and label sketches. And for the node and link sketches, we do traditional post-processing to get the adjacent list of this query graph. And for the labels, we do this label recognition to get the label for each node, and we combine them to put them into a graph embedding, and that will return the vector of the a vector embedding of all the graphs, and we can use the cosine distance to find the similar graph for the query graph. So here is the detail of each module. For the sketch segmentation, we take the input of this sketch image, and we output for each point on this sketch. We output the label for it. So here we use a numeric encoding where 0 indicates it's a node stroke, 1 indicates it is a link stroke, and 2 indicates it is a label stroke. On the right hand side, I use a example of an airplane sketch where the first line indicates the x-axis, the second line indicates the y-axis, and the third line indicates its label. And the second part, the node label recognition, the input will become a monochromatic handwritten image that describe a mathematics expression that can be obtained from the label stroke, and we connect the stroke and make it as a bit set of that label stroke. And the output of that should be a LaTeX expression that encodes the input image. So the right hand side example shows, we input this monochromatic handwritten image, and the output will be the square root of 48. The third part is the graph embedding. So we input a query graph G query, and all the processed dataset all the processed graphs, and the format will become as for each graph, the format will be the number of vertices, the number of edges, and then starting from the next line, each line represents a vertex starting with its label and then its degree and all its adjacent vertices. And the output will be an embedding vector for each graph. And the basic idea will be input the graph. Given this input graph, we first learn the node embedding for each node, for all the nodes, and then we literally sum up all those node embedding as the graph embedding. And what I have already finished is the reproduce those 3 modules. And for the sketching, we achieved the accuracy rate in terms of pixel 94, and the stroke accuracy 88. And for the BTDR, which is the label recognition, we achieved the accuracy rate without any error 53%. And the graph embedding, we perform a unsupervised classification task, and the accuracy is 91%. So the challenge is the first the main challenge is that we need to synthesize the sketch images for the processed graph in the graph city. And the second challenge is to connect those three network, including solve the environment, because the PyTorch version between these three repository are different. And the third one is that the to post-process the adjacent list, that will need to find the nearest meta-node stroke for each meta-link strokes. And that can be done by use the traditional data image dilation for each link stroke. And here is the timeline. And the expected deliverable will be an application that records the user's stroke of the sketch as the input and output the name of the graphs that are similar to the input sketch. And here is the reference. Thank you.
Okay, thank you very much. All right, please stop sharing your screen. And can group 6 imitation learning please share the screen? Yeah, if there are questions at any time, please just put them in the chat, and then we can I can raise those questions. Okay. All right. So if there are no questions, group, you can begin.
Okay. It is my cross-domain imitation learning with the spatial temporal data project. Okay. Let's start with some preliminaries. First is MDP. MDP provides a mathematical framework to model decision-making process where an agent interacts with the environment in a sequential process. And in general, we represent MDP as a file tuple, SATR gamma, as its database is action-based space, and T is the transition probability. R is the reward function. Gamma is the discount factor. It's a positive number between 0 to 1. And we also have pi. Pi is the policy function. Have the trajectories. Tau. Tau is from S0, A0 to SL, AL. L is the terminal time step. And in our problem, we will divide the tau into two parts. The first is tau e, is the export trajectory. Another one is tau ne, is not export trajectory. And we also have the pi e. Pi e is impractical policy from export trajectory data. And in MDP, we always want to calculate the expectation with respect to the trajectories. Okay, in this equation, and we also for each agent aims to minimize its expected reward is the expectation about R. Okay, then is the LL. LL is aims to inverse learning reward function R and recovering expert policy pi based on the various principles. For example, they want to maximize the Maynard's H, such as this, and based on the different principles, H could be somehow such as cross entropy, cross causal entropy. Okay, and do the LL have a very powerful method means GAL. GAL is a generative adversary imitation learning, and for GAL they add some Jetson divergence to the and after add this, they can use GAN structure to train this. The generator network is representing the policy function pi, and the discriminator network to represent the reward function R. Okay, some background. And for our problem, we use MDP. MDP in the S of MDP is a geographical location is GPS, and temporal information, you can see the picture is S0, S1, and so on. And A in MDP is spatial temporal decision. You can see the green part of the picture. And the human agents decision-making strategy will be modeled by the Pi and R. It is something we want to model. Okay, so the input will be given some mixed demo from both expert and non-expert is T or tau divided by tau E and tau NE. And something we want to do is first is distinguish tau E and tau NE from tau, and then disentangle expert knowledge from tau E, then extract the state related information from tau NE, and finally we want to infer the optimal decision making policy is type. Okay, and there are some existing solution framework. They do the whole framework to 3 phases. The first is data processing. The second is expert knowledge disagreement, and the third phase is policy inference from non-experts. And the modeling part is mainly on the phase 2 and phase 3. And in our project, we want to try something new algorithm in the phase 2 and phase 3 to instead of GAL-based method, we want to try OT-based. Okay, it's our idea. And for now, we have implemented the solution framework we mentioned, and we reproduced the baseline GAL and CGAL with the small GAL data, and show they have some results like this. We use the taxi driver trajectory data. Okay, and for the next step, we want to implement the OT-based method in the framework, and do the experiment in large-scale data. We want to do this in 2 weeks, and after that, we want to do some bonus. They have some challenge. Bonus is beyond the existing framework to fine-tune some setting to make the OT method have more powerful. In some other areas, such as vision and robotics, this shows OT method will have more powerful than GAL-based method. We want to try this in the spiral temporal data. Okay, that's all.
Okay, thank you so much. So since we have maybe 1 or 2 minutes, are there any questions? So maybe I have one quick question. So can you go to your plot of comparing C-GALE versus GALE? Yeah. So can you just describe, for the group, can you describe intuitively what are the differences between the 2 approaches, and just any insights from this initial result? So like it sounds like C-GALE is outperforming, right? And GALE is just plateauing. Is that right?
Yeah. The GALE is, as I mentioned, it's a very basic method for the GALE-based method, and the C-GALE is a baseline, and we can say in this picture they have epoch and KL divergence. KL divergence means the inferred optimal policy generated trajectory between the ground truth trajectory. We use taxi driver data. They have some taxi driver have some ground truth policy, and we want to compare with this. And in general, the KL divergence is we can say it as a loss of the we can say it as a loss matrix. And the C-GALE prefer better than GALE. I think one reason is the C-GALE is truly better than it, and another is we just use small GALE data, and it's so small, so the performance is not very better. I guess if we use some large GALE data, the performance will be better than now. It's just some try to show our implementing is right. Okay.
Okay, thank you very much. All right, so please stop sharing. Is group 7 impact prediction present today?
Okay, thank you.
Yeah, thank you. Matthew, are you present? I don't think so. Okay, so group 8, music driven animation. Group
Hey,
8.
Professor. Yes, I am sharing the screen.
Okay, wonderful. Yeah, ready whenever you are.
Okay, so the topic for our project is music-driven walk cycle for humanoid character. And first I'll start with the technical approach that we will be doing this for the project. So we have divided our project into 3 steps. The first step is the collection of the MIDI files. So MIDI is basically music instrument digital interface. So instead of working with the audio files, it would be better if we work with the MIDI files so that we can extract a lot of music information from the files, and it provides a bounty of information which will be useful for the later stages in our project. And after the collection of these MIDI files, our next step is basically extracting beats from those files. So we read a lot of papers on how to do that, and we also researched a lot of libraries may be available. So we are basically using the Python language, and there is a package available that is Pretty MIDI Python library, this library can be used for creating, manipulating, and extracting information from the MIDI files. So it's actually useful for us because since we only need the beat information from these files, this library has been a pretty useful thing for us. And the next step would be that after getting those beats from the files, we need to map those beats to the motion of the character. So we will be representing the joints of the character according to the beats of the music which were extracted from the previous step. So these are the approaches we will we have followed and will be following in the next steps. So now I'll talk about the Pretty MIDI library package, which is in the Python. And this library is actually very useful even in terms of creating these MIDI files from scratch. Instead of depending on the internet to collect the data, MIDI files data, we can actually use this package and create our own MIDI files. So as you can see, I have attached a snapshot of the code. So this is a basic template. So for every notes, since there are different notes in music, so for every notes, we can just set up different pitch and different start and end of those notes. So using these variables and the notes and velocity, pitches, and start and end time, we can create our own MIDI file. So it gives us a lot of flexibility in terms of creating MIDI files, basically. So it contains classes for handling MIDI data. So that's in the format which would be easy for us to extract, and we can also create MIDI files from scratch. So we have written this code in the Jupyter notebook, which we have uploaded in the GitHub repository also. So by using this IPython display, we can actually listen to the audios, the MIDI audios also. Also, we can parse an already downloaded MIDI file. So it's very simple. You can just use a class of that Pretty MIDI, and you can just give input the MIDI basically. So for example, I have teddybear.mid file already. So I can just pass in that package and I can use that. And it handles all valid MIDI files, and it will raise an exception if the data is correct. So it also throws an exception if the MIDI file is not correct. So by using the Pretty MIDI object, we can actually learn a lot about the audio file. So as you can see in the first step, we just create an PM, which is the Pretty MIDI object. And using that Pretty MIDI object, we can see the time signature changes and also the instruments that have been used in that audio file. So there can be instruments like piano or drums. So it also indicates those kind of instruments also. And for every instrument, you can also see the notes, the pitch bends, and the control changes. These terms are related to like music field, and it's just an to if you want to gain information about every instrument or how the pitch is changing or how the notes are being used in that audio file. So this library is pretty useful for that. Also, we can plot a piano roll using this Pretty MIDI package. So piano roll is basically, it contains perforations, and you can use this information while you are playing a piano. So it contains a list of notes in every timestamp. So basically, so you can actually play a piano just by seeing those notes. So I have written a function which will display the nodes that are being used in that MIDI file. So this is also a useful information which can be extracted by using this package. And the main thing that we need is the beats. So for extracting beats, they have these direct functions called as get underscore beats and get underscore down beats. So there is a difference between a beats and down beats. Down beats will be related to the tempo changes as well as the time signature change events, and beats is according to the only to the tempo changes. So there are two kind of beats, the normal beats and the down beats. So these can be extracted from the MIDI files by using these two functions, and these two functions will take input parameter as the start time. So ideally the start time is 0.0 since we want the information from the beats from the start of the MIDI file. And it returns NumPy array. So it will just include the timestamp, basically the location of the beats, and it will be in an array. It would be in seconds. So we just get directly an array which will be having the timestamps of the beats. And similarly for the get down beats also, it will take the input as the start time and output as the NumPy array, which has the timestamp of the beat locations. So this is the main function for showing the beats. So in the graph, you can see for every timestamp, you can see the white line shows the beats, and the gray line also shows the down beats. So this graph will basically show where are the beats and the down beats in a given time period of that MIDI file. And if we just display the beats array, so it will, you can see a big an array which contains all the seconds representing where the beat is actually. So for every audio, there will be different beats array. So this is the main basically for our project, the extracting the beats and the down beats.
Okay, so I will continue from here.
So maybe just another minute, okay?
Okay. So in addition to Pretty MIDI, we have also explored other packages like Music21 package. So apart from what we are able to do with Pretty MIDI, we can also plot the notes of the music. So let's say, so the beats is the unit of time in music. So for each bit, we can know what are the notes in the music, and also like we can plot, like we can get information like present in this graph where different points denotes different notes at each bits, and we can use this information to get which notes are being played at every timestamp, and we can extract emotions from them. The next slide. And also we can also extract pitch from the music. So pitch represents the loudness of a music, and there are different pitch class in music. So for the pitch class with high frequency, it will indicate that the music is related to excitement and happiness. And if it is a low pitch class, which means that low frequency music, so it will represent sadness and depression. So we can actually use this histogram to see which high pitch class, like if in a particular music high pitch, if the number of high pitch class is more than the low pitch class, then the music is like happy, like it indicates happiness or excitement. But since we need for each timestamp, we want to generate a walk cycle for each timestamp, then can you go to the next slide? Next slide. Yes. So since we need for each timestamp, we can also get the pitch information for each timestamp, and we can essentially use this to get like whether the particular timestamp contains a high frequency pitch class or low frequency pitch class. So these are the features that we can extract using the libraries. So yes.
Should I continue, or are we out of
Yeah,
time?
time's up. So just maybe one note on the animation side.
Yeah, so as we know, the downbeats and upbeats, we will have these four keyframes, and we will map these to the beats. And after that, we can add more keyframe animations for the downbeats. And next slide, please. And after this, we will create a motion signal, and then we'll map it to the signal. And we can also try actually plotting each joint in matplotlib and just map it to the beats, but as we know, each second of the beat.
Okay. All right. Sounds good. Thank you so much. All right. Please stop sharing your screen. Let's move on to group 9, one short story.
Yeah, I'm sharing my screen. Yeah, can you see my screen now?
Yes, please go ahead.
Yeah, okay. Yeah. Okay. It's not loading. Is it fine if I just show the slides?
Yeah, that's fine.
Yeah. Okay. So currently our state
just maximize the window so we don't see it. Go ahead.
Yeah. So basically our project is now divided into 3 phases. One phase is getting a caption from the input image, generating a paragraph from that caption, and extract objects which we can put into the image which we want to make the output from. And currently the caption generation phase is working fine. In the generation of story from the caption, we are getting a story output as intended, but it's right now a very slow process and a very heavy process. So I'm looking at different options to either create an alternate route to this, or just removing parameters which do not affect our model. And the next to do in this phase will be to basically get to know, like basically extract all the main components from the story, which we can put into the output image. And yeah, so yeah, the challenges which I right now described, yeah, so then generally these are related to the story generation thing. And as you can see, the outputs, like from the captioning model, we are getting these outputs. And for the story generation, we are getting outputs pretty relatively similar, relatively consistent with the thing we were supposed to handle. And I can also show you how it works on this one. Yeah. So basically I fed an image to this model and it can basically give a pretty good caption. I would also have shown the story generation part, but it's right now too slow to appropriately show in a slideshow. And Diwakar will go on for the next.
Yeah, I can share my screen.
Yeah.
Okay, can you see the PPT?
Yeah.
Yeah, okay, so coming to page 2. So what we have identified is that we have to limit our objects vocabulary, and we need to come up with some common objects. And this is what the vocabulary looks like. It consists of some certain common occurring objects that we are trying to consider for our story. So that is the object vocabulary part. And then what we realized was that generating a sketch just from the text prompt doesn't always give consistent results. and the output can look very different, and it may not look meaningful and relevant to the input object text. So and then we realized that having a reference image as an input gives better image output in terms of geometry and the context. So I can show you the challenges that we faced. So even for a very simple object like ball, we do not get a very good output. And then there is another hyperparameter for generation, which is the number of strokes, like the number of curves that we want for the generated output. So even with different strokes, even for the simple object, we're not getting very good results. So that is one challenge. And here, the next challenge is like, it can be too abstract. Unless we know that the prompt was horse, it may be difficult to tell what this object looks like. So what we conclude from here is that it's not as contextually similar that as we had imagined. So it can be too abstract sometimes. And here is another object for chair. And it doesn't look like a chair at all. So it may be making sense for computer, but for humans, it's not what we would expect. So what we concluded was having a reference image gives better output images. So here is an image that we tried to generate for house, and this is what we got. And this is what having using a reference image looks like. So the interesting point is, even if we have the same reference image, we do get variations in the output. And that is one good thing, because we would want to have a varied output. And yeah, this is just a demo. So this was the input image and this is the output. Now this could be improved upon by changing the number of strokes and also increasing the iterations, but doing so will take more time. And then what we identified was there is another data set which would be better to use, which is Quick Draw dataset, and it has a lot of objects. Again, this is the vocabulary for that dataset. It has some 345 commonly occurring object, and each of the objects have some 500 images for that particular class. And yeah, every time I do that, it's going to randomly pick one of the images. So one way is to have a generated image corresponding to that quick draw image. So it works fine, but what we realized was, since this is already a line drawing, why don't we just use this now? Because it will save us time, and it will also give us bandwidth to focus on the phase 3, which is like placing these objects in a meaningful way. So our initial agenda was to have a drawing so that we can have more control, and it could allow such kind of overlays. And that's why we wanted to use a sketch for that. But we can use the quick draw object itself. So what we plan to do is we take this kind of an image from quick draw and make it as a transparent, add an alpha channel and have a transparency in the background. So what would allow us to do that is it will allow such kind of overlays between two objects. And having such overlays will give us more flexibility on where to put the object. And it will not leave a square patch when adding an object. So that is what the intention is. Yeah, it's almost done. Oh, so the issue was I turned on the mask object, and that's why we had an issue. But yeah, that is what the idea is. So going forward, coming back to the PPT. Yeah, so line drawing is not as controllable that we had imagined. So what we're switching now is to quick draw, and using this, it will allow us to move to phase 3, which is how to place a new object in a meaningful way. Yes, there was another challenge that when we need to control the number of curves or the number of strokes here, how would we decide that how many strokes do we need for a particular object? Because for a ball, we could draw a ball using 2 or 3 strokes, but for a complex object, we might need some 10 or 15 strokes. So that was another challenge that we were facing. Yes. So this is the progress so far. If you have any questions, you can let us know.
Great, thank you very much, and I really appreciate the live demos. Okay, wonderful. So yeah, please stop sharing your screen. Yeah, I have several comments for you on Canvas. So if there are no questions about this project, let's move on to group 10, the Pyramid GAN project.
Okay, thank you, Professor.
Yeah, please go ahead.
Everyone, I'm Richard, and here is my, and here is my AAP GAN for graph image generation, and I will introduce what I have done in the past 2 months. First, we selected the bigraph GAN as our backbone as well as baseline. According to the paper with code, it's still the SOTA model. And what we have to mention here is that it is significant innovation is the bipartite graph reasoning blocks, and our structure maybe can add it to here to replace it. And to replace several blocks of it, we have two plans. First, we can replace the original bigraph blocks so that we can capture the relationship between the source pulse and the target. Or we have plan B, is the IA blocks to enhance the feature of the input images and the map of the relationship between the two pulses. And we tried the plan A first. To verify whether our plan A works, we introduced a modified APNet for REID to the original backbone. And since time is limited, I will share the demo code later. And our experiment carried out on 2 data sets, but our test is based on market first, since market is much smaller than deep fashion. Deep fashion tends to spend about 3 days to train and test. And since the loss function cannot reflect the quality directly in our image generation field, we set up some shell script to automatically get the matrix and test for. And the following five matrices are for evaluation. And here is the ground truth image, and this one are the. Here we have the output of the shell script. As we can see here, if we add 5 structures to the AP structure to the baseline, it will have an improvement of more than 5%. It is really a significant improvement on such an SOTA model. But here we also have some challenges. As I have mentioned before, the paper declared that they have a SSIM score, the structural similarity score of 0.325. But if I train and test by myself, it can only reach the 0.306, which means our improvement is based on the baseline that's trained. And so it is not comparable to other SOTA modules. It's still so. And there are other problems on the existing APNet. First of all is that it uses both spatial attention and channel-wise attention. The CBAM, which also used both the channel-wise attention, has already been introduced to GAN, to our field, so that we prefer not to reuse it. And secondly, the original PANet only used the path of one direction, but there are a lot of improved versions that use the two direction. So we may try to add a bottom-up path. And third is that each layer of the APNet treat each layer equally. So in the future, we may add adaptive mechanism to further improve the structure. Also, there are several steps here to that the to-do list here to solve this problem. And by of April, I will probably finish the structure and make it perfect. And the remaining days of I will write the paper, the report, and prepare for the presentation. Deliverables will be an associated model, a technical paper, and the presentation. Let me share a screen of the code, the demo is here. Here is the model variance, and the input is all inputted to the model. As we can see here, the model is a graph model. There are the backbone from the original background protect graph GANs. The graph model takes the input image and the source pose and target pose as an input, and they also it is made up of several blocks. The graph blocks, which means the original paper used GCN here to capture the relationship between the input pose and the target. So our improvement will be on the graph blocks. We added our blocks here. If add AP is equal to true, we will add some baseline blocks. The APNet here, so that we can capture the relationship between the input pose and the target, the source pose and the target, and also where we need to modify further improve is this place, since it used both the spatial attention model and the channel-wise attention model, but it has promised a good improvement on the backbone. So if we further improve it, maybe it will have it will further have an improvement. Okay, thank you. That's it.
Okay, thank you very much. Please, yeah, great presentation and appreciated the live walkthrough of your code. So let's yeah, please stop sharing your screen and let us go to group 11, speech to image.
Hello.
Yeah. Please go ahead.
Hi. So we're going to do a quick presentation on our progress up till now, and also discuss what our architecture of the model is and a few other issues that we faced until now. Okay, so firstly, let's discuss what we're trying to do here. We're basically trying to predict facial expressions of a person just by listening to the sound of that person. So to achieve this, this is an overall outline of a model that we've thought of. Having said that, this might change because as we're moving forward, we're realizing that this task is pretty heavy computationally, and it's taking us quite a lot of time to do things. So we might have to take that into consideration and change our models. But for now, what we're doing is we're taking audio files as well as video files and pre-processing them. So and then we're sending them to the neural network, which consists of CNNs and one layer of GRU. We're putting in another test data, which is an audio file into this GRU and giving out facial landmarks as results of this network. Then we're feeding those facial landmarks to a GAN. For now, we've kept this as DC GAN, but we might change what GAN we use eventually. So we're taking this as an input to GAN and also sending in real images and landmarks to GAN to give us a final expression of a person. Moving forward, so this we've kind of divided this project into two parts. We can say this is the first part would be speech to landmarks model, and the other one would be landmarks to images model. So for speech to landmarks model, like we've said, we take audio and the video as the input to CNN and GRU model. We extract voice features from the audio by using fast Fourier transform. And then we also extract landmarks from videos. But before doing that, we actually split videos into by frames. So we have images out of videos, and from those images, we're extracting landmarks. And then the CNN model takes in the time frequency spectrograms of audio signals as test input, and then using GRU as the final layer, we're generating landmarks as the output of this particular model. And then taking the output of that model, we're and giving GAN real images as well, we are going to predict facial expressions as the output. So all of this is just repeating what I have already said or explained in the architecture. So the current status is that we have successfully pre-processed audio signals and images. So like we said, for that to pre-process audio signals, we used fast Fourier transform, and by images I mean videos. So we split the videos into images and then generated landmarks from those as well, landmarks specifically of faces from them. And like we've said, we've decided the model architecture. The main challenges, like I've said, is computational challenges. To be very honest, we did not expect it to take so much time and resources. So just the pre-processing of our data has taken quite a few days, and also figuring out how to pre-process audio data, because we have never worked with that before, was kind of challenging for us. The next steps would be to train our GRU and CNN model, and once we're done doing that, we will finally have to train a GAN. So this is a rough timeline that we've given to complete this task and give out a presentation by the stipulated deadline. And the deliverable that we're trying to give out is a model that predicts facial expressions using audio signals, and we've still not, we might, if time permits, we might incorporate giving in short videos as well, and not just images. But we will definitely be giving out images as outputs and proof of qualitative results, and also some standard metrics to demonstrate some quantitative results as well. That's about it from my side.
Okay, thank you very much. Yeah, so I have several questions or several comments for you on Canvas. Generally, okay, so you're spending too much time on pre-processing, is it?
Yeah, so the problem is that we have say about 3,000 videos that we need to pre-process.
Yeah, okay. So so I've given you some suggestions, but in general, maybe you want to slice your data, right? So start off with a smaller data slice and try to overfit something, right, before you process the entire data set. So you don't want to spend too much time on step 1 and realize you're making mistakes, and step 2 and step 3 later, right?
Okay.
So think of overfitting with a smaller data set.
Okay, thank you.
All right, thank you so much. Okay, let's move on. Group 12, star semantic.
Okay, wait a minute. Okay. Let's start play. Hello everyone. My name is Haonan Chang. Sorry, not this one. This one. Hello, my name is Haonan Chang. I'm doing my project called Semantics Scene Level Tracking and Tree Construction. First, I want to introduce the problem. And the problem is, like, given the set of RGBD images, we want to reconstruct the geometry and tracking the position and deformation. Label the semantic information for each individual visible object in the scene. So this is the problem. And before we introduce the algorithm we are using, I want to introduce several concepts in the graphics. So the first thing is surface, which is the short for surface element. This is a representation for geometry. Surface can be regarded as an extension of a point. One surface can have multiple attributes at the same time. Well, for example, color, normal, or position. Many surfaces together, they can form a surface. So that's why they are called surface element. This is surface. And the other thing is deformation graph. This deformation graph is a structure to represent the non-rigid deformation for geometry. Because what we are doing is like largely non-rigid scene reconstruction. So we need this deformation graph to represent how a scene is deformed. So in non-rigid deformation, every point in the geometry has a different deformation. For example, the rotation, different translation. So we use work field to describe the whole deformation. It's like a field. Every point has a different value. It is impossible to log the whole work field at every point. So we will store the deformation in the deformation graph. Every node in the graph has a position, a deformation, and several neighbors. And the deformation of any node, any point can be computed from interpolation of its nearby nodes. So this is the deformation graph. So this is some preliminary conceptions. So let's talk about how we are solving the problem we proposed at the beginning. So we use several things to represent the model. A surface-based geometry, ST, a deformation graph, GT, a work field, WT, a historical maximum distance, DHT, which is a distance matrix logging the interdistance between nodes, and the semantic label LT to describe the model. The measurement comes from, let's say, 3 RGBD images. So basically, in each time step, we starting with the model and the measurement. The measurement will be fused together and generate a measurement fusion measurement M. And by using a neural network, we got the labels LM. And all of those things are combined together by putting into a process called non-rigid alignment, through which we compute its current warp field. And then everything will be put into this structure pipeline called the geometry fusion. In this step, we align our current geometry with the measurement, improving our geometry. And then we will generate the model for the next frame. You can see here. And output in each frame is like we can segment our existing model into different for each individual object. So this is basically that's the method. And current progress is, well, we have finished our baseline method, which is the scene level tracking reconstruction without semantic information. So the next step is to add the semantic information into the current system. And we further improved our interactive demos and post them on our GitHub. So let's see some qualitative results from our baseline methods. So this is the first example. Here we are using, you can see here the table, and on the table is a plushie toy. And we pick up this toy from the table, and you can see here is how the segmentation is happening. The right is our hand, and this is the toy, and this is the table. And well, at the beginning, their topology belong to the same. So they are the same color. And after we lift it up, you can see their topology are splitted. So they are labeled with different color. And this is the final result. And you need to know that along this process, we didn't use any semantic information, which is we are planning to add in the future. And this is another example of object rearrangement example. Here are 3 objects here, and we rearrange their position in the final frame. And you can see throughout the process, everything has been correctly segmented. And this is another example on lifting a scarf, which is very deformable. You can see this is the initial frame, and this is the target frame. And this is another example, a more complex example, where we lift this bag, which contains a cracker box, and we put it on the table and lift the box from the bag. And you can see how the segmentation is happening along the time. And this is the final segmentation for each object. And we also compared our reconstruction result with other non-rigid reconstruction method called servo warp. And you can see this is our result, and this is the servo warp's result. You can see our result outperforms both servo warp with global reinitialization and without global reinitialization. And here are some interactive demos for our baseline method. We can see here is by clicking this, it comes to my GitHub IO, and you can see we can directly visualize all of those things online without installing anything. You can just open this web page and you can visualize our result online. And let's go. And finally, we have some challenges currently. So the first thing is the choice of proper semantic segmentation network, which we have found the recent work by NVIDIA, the frontier network is very useful for us. And the second thing is how to combine the semantic information into the existing system. So basically, we are using this in 2 ways. The first is we are using as a topology prior, and the other is we are using this as a semantic label. And next slide, and final delivery. So in this week, we will test different segmentation networks to test those methods. And the next week, we will prepare for the integration code, and then we will keep improving our system, and then we will prepare for the final reports. So basically, that's it.
Okay, thank you very much. Really,
thank you.
Yeah, really appreciated the interactive demo. Okay, let's please stop sharing the screen. So let's move on to group 13, virtual try-on. Yeah, please stop sharing your screen so that the other group can share. Yeah, group 13, are you there?
Yes, Professor. Can you hear me?
Yeah, go ahead.
Yeah, so like let me just quickly start the timer so I keep track of the time. Okay, so it's just loading, 1 second. Okay, let me just give it like this. Okay, so yeah, so our topic is virtual try-on. So no, the slideshow is not working. Okay. Yeah, so our technical approach, like we discussed in the previous presentation, consists of 6 stages, out of which the first 3 are basically the pre-processing stages itself. So the first one is, of course, generation of segmentation map. Open pose we are using to generate a pose map, and finally we combine these two to get image agnostics. And the 4th step is the segmentation generation, where we try to get a segmentation map with the person wearing the cloth, and 5th would be the cloth deformation, and finally we can do the last step, that is alignment over segment normalization, where we try to fix the invalid misaligned or deformed areas in the person's key point. So what we're basically trying to do is we have a Wheaton HD model, and it requires this listed parameters as its input. So first one is the reference image, which is the person itself, the cloth image and the cloth mask. The 4th one is a past image of the person, and the 5th one is the pose map, and the 6th one is the pose key points and the JSON. So what we currently have is we have the segmentation generator. We have geometric matching model, which is nothing but the cloth deformer, and we have the alias generator. All this pre-trained model we already have. So what we basically need would be the pose map from some model, and the segmentation map. I mean, again, that can be also from some other model. So in Wheaton HD, they have talked about part grouping network, which is used to generate the pose map, and open pose is used. Part grouping network is for segmentation map, and open pose is used for generating the pose map. So if you can see this image, so here we can clearly see the process that we are actually trying to get into. So we are currently at so the next, the current status is where we are trying to extract the segmentation map, which is this particular image, and we're trying to extract the pose map. So this is where we currently are right now. So we need 2 different models for this. So first one would be the PGN network that I talked about, which requires a reference image and the edge images, which was actually implemented by implemented in MATLAB. So we have somehow gotten it to converted it to a Python code and have implemented it as well. So that's working. And the open pose, which we have, which is an open source library which is available in Git, but it's actually an exe file which we get right off of the bat, and we have to generate the Python API for this, and that is used in CMake. But yeah, so we are at that stage as of now. So yeah, the next stage is the quantitative result that we have done. So Andrew will go ahead and do it. Let me just.
Hi, hi everyone. So thank you.
What's going on? Have you all figured out your issues?
Can you hear me?
Yes, we can.
Yeah. So like Aditya mentioned that currently we're testing out pose map and segmentation models. So the open pose model for pose detection took approximately 2.6 seconds for a single image, which is quite expensive. But this is based on the exe file that we have. So we're trying to convert it into a Python script, which will help us because we can load the model initially and then use keep it as a cache, and then eventually the processing would be much faster thereafter. And the second thing is the segmentation map. So we tried out different segmentation models because we don't have a specific model that we can use that was used in V2NST. So like we focused on two different models. Like one was instance level human parsing, second was the self-correction for human parsing model. So the first model took approximately 5 seconds per image, which is also very expensive. But this was without using the GPU. So and this particular model is very it's giving very good results compared to the second model, which is taking less time. So there's a trade-off between time and like performance time and the quality that we're getting. So we're focusing right now on picking the best model and maybe improving the segmentation model so that we have better results at the end. So yeah, this is some qualitative results. So we have these two segmentation and pose map we are getting from the OpenPose and the instance level human parsing model. So yeah, we tried out some custom images of parcels, and this is the stage currently so we are given we have these reference images, we have cloth images, we have cloth masks. So currently we are focusing on like the existing cloth images and cloth masks. We are not focusing on trying to implement this like generating these cloth masks. So our main goal here is to get the pose map and the segmentation map. So this is the existing test images that were provided as part of the V2NST model. So as you can see, there's a difference. So so this is giving us quite better results as compared to this particular model. You can see there is some misalignment and there are some distortion in the image. So we are trying to figure out like what are the improvement we can do in this particular scenario so that we can get better results. So currently we have two major challenges. Like one is to convert the OpenPose into a Python script, and second is so basically the input to the V2NST, which is basically the segmentation map. So it is we are getting it in the form of 4-bit or like not exactly what the V2NST requires. So we are trying to convert into 8-bit image, which is palletized mode, and so that we can run the end-to-end pipeline by ourselves. So I think Harsh will continue with the planning steps.
Yes. Hello, everyone. So I would like to conclude here. So far we have two deep learning models. One suggested by the Wheaton paper that we are initially referring, which takes 5 seconds to process the image to generate a pose map and segmentation. And this is built in. This is the reason for this is because of TensorFlow 1x, and it's not using GPU. The second one is self-correction human parsing model, which takes around 0.6 to 1 second to process an image because it uses TensorFlow 2x and we are using GPU there. So we are here deciding that which model to pick. For the second model, we have a constraint that we have to process the API using CMake. So for OpenPose, we are in the process of generating an API using CMake. Once we are done with it, we will be able to generate the segmentation pose for the OpenPose model, and then we will get better results. So can you go to next slide? Yes. So once that is done, we will be in the stage of swapping clothes from the pose. And once that state is achieved, then our plan is to create a simple web application using Streamlit, which will take an image from a video, like from the webcam. And once that image is taken, there will be different pairs of clothes to select from. And once you select a pair of clothes, it will just swap it from the image, and you will get the try on method from there. So can you go to the next? Yeah. So that's our end goal. Now Aditya will give you a demo for the initial posing.
Yeah. So here is a small demo. So in OpenPose, it was pretty straightforward to generate the result. So as you can see, I have just put our images itself over here, and with just a single command and
I don't think we can see the demo. Okay, we can only see your Google slide.
Okay. Just a second. Yeah. Is it visible now?
Nope.
Yeah. So I guess it's visible now, right?
Yes.
Yeah. So yeah. So in OpenPose, it's fairly easier to run the data. So I have just our images over here, and I just have to give the path, and it just generates the poses for me. So as you can see, I have the poses. Yeah, this is fairly straightforward. But the segmentation one, which is the one that is actually taking a lot of time. So if I run the test PGN, so this is where it generates the segmentation map for us for the Wheaton HD model. So yeah, so and again, this is in 1x, and it's not using GPU also. So we'll take maybe a minute to process 3 images that I have given as input. Yeah, so here you can see the output of the result. So yeah. So this is what we are planning to go ahead with.
Mm-hmm. Yeah, no, this is really great. Okay, so yeah, y'all are quite over time. Okay, so unless there's anything to add, I think we can conclude here.
No, that's all.
Okay, right, wonderful. No, thank you. Very nice presentation. Always appreciate the live demo. All right, so please stop sharing your screen.
Thank you.
Last group 14, VR space design.
Yep. Let me share my screen. One sec. Can you see my screen?
Yes, please go ahead.
Okay, cool. So yep, I'm VR space design. Essentially what we're doing is creating a city environment to test participants' behavior across different scenarios in VR. the participants, when they start, will be told that the city that they're in is either a low vaccination or a high vaccination rate. And to test the participants' behavior, the city will be subdivided into different spaces so that each space has a specific scenario that we're testing with the user. So for the technical approach, what we're trying to do is, since we're trying to understand the social forces involved in like a pandemic scenario, each of the different spaces will have different variables assigned to them. So for example, one of the things will be non-player characters will exist in different, in each of the different scenarios. Some of these non-player characters will be masked. Some of them will be having different animations running. So one could just be walking around, another could just be idle, and so on. And then the other main component will be physical objects that the the participant can interact with to test to see how a person might interact with different parts of their environment, depending on if the city they're in is a high vaccination or low. And to build this out, I'm using Unity and the XR framework that they provide. And I'm pulling art and sound assets from the Unity Asset Store. And then I added in some custom elements such as face masks. And some of the animation is coming from Maximo, the open source animation library. And then the city environment itself is being custom generated with the help of my research mentor, who is helping me figure out how to build out the specific spaces. So for the current status, right now I've created the XR rig and started to add in the different scenarios. So for the participants, they can start walking around. They can teleport if needed. And then they can already start to pick up all the different objects within it. And then finally, I built out a logging so that we can track where the participant is within the different spaces, and then also their view direction so that we can then use that data to understand what they're doing across participants. One other thing is right now I'm also working with my mentor to come out with what the actual scenarios will be. So I have a basic layout just to test all the different options so we can quickly iterate through them. And I've also set it up in XR. So this is just the basic XR setup at the beginning with the controllers and so on. And then the instructions are already there. When the participant logs in, the high vaccination or low vaccination rate will be provided for them so that they know which one will be a scenario. And then they also have instructions on how to use the buttons and so on if they've never used VR before. And then they can start, some of the environments starting to be built out. It's the art assets, as I said, are coming from the Unity Asset Store. And the way the environment is being laid out is each of the spaces is mapped to the available space that we'll have for the participants. So it's, I think, 4x6. And so they'll be able to walk around the specific spaces as they're walking around in real life with the VR on. And then the next component is to move from one space to the other. They can teleport. So the idea behind this is when they move from one space to another, they'll teleport so that they can walk back through the space itself. So that's why they're turned around. So when the participant starts, they'll walk through the space. And then when they're going to the next one, they'll teleport and be facing the other direction so they can walk back. And in this way, it tries to keep some level of immersion. And then, yeah, some of the non-player characters have already started to be put in. I'm getting most of the art assets from either Maximo or the Asset Store, and then the animations as well. And this one is a character without a mask. And then also a non-player character with a face mask to see if that causes participants to change their behavior at all. And then finally, there's some interactive objects. It's mostly through picking up through colliders so that the participant can like choose or choose not to interact with objects as they move through it. And then And then the final thing is they can reset the whole scenario and then start over from the beginning. And so the goals from this are from the logging data, what we plan to do is generate heat maps to understand what the common areas participants are gravitating towards. And that way we can understand where participants are more or less comfortable walking within like specific scenarios. Then the other thing I plan to do with this qualitative data is do some clustering to capture behavior across different participants. And then also do some screen capture as a qualitative step to see what participants are looking at when they're in a specific space. And finally, to have a survey so that we can capture their sentiment as they walk through the city and how they felt depending on the two different low and high vaccination rates. And then, yeah, so for the current challenges, the big one is just random XR glitches and compatibility. In my personal space, I'm using HTC Vive, but for the final demonstration, we'll be using, for the final participants, we'll be using Oculus Quest 2. And there are some differences in the XR framework in getting like buttons to press and creating builds and so on. The other one is making sure that the spaces have proper constraints for them. So making sure that we're putting in the right variables for the spaces to make sure to capture the right variables. And then the last one is just making it realistic enough to make sure we get the responses accurately. And then for the next steps, the main focus is going to be on building out the multiple spaces. So I'm going to work with my research mentor to build those out in the next week and a half to 2 weeks, and then add in some sounds so that it feels more realistic, and then QA it, and then actually bring in the participants for the final stretch before doing an analysis to produce the final results. And then, yeah, at the end of the semester, the goals will be to have a fully fleshed out VR city environment, have the experiment results, and then produce a final paper.
Excellent. Thank you so much. Yeah, general comment. I mean, I'll give you several comments, but general note for you is you could consider doing a pilot study with this class. So you may want to consider that. Okay. All right. But yeah, I think that brings us to the end. So what did everyone think about the quality of the presentations today? Any just reactions? Thumbs up, thumbs down, heart, emoticon, I don't know. Any thoughts or comments on the general quality of the presentations? Nothing? Okay, all right. I was extremely happy. Yeah, great job, everyone, right? In general. I was trying to be quite critical in my review, but I couldn't find too much fault. So yeah, no, overall, excellent job, really appreciated. Yeah, Harsh says all presentations is good. Yeah, yeah, overall, excellent job, really appreciated the demos, the results, right? And I think, yeah, most teams, if not every, seem to be well on track. Yeah, Max says that everyone seems to be progressing well. So yeah, great job. Really no complaints. Keep up the good work. I've provided several comments to the group. So please take an opportunity to look at those comments and try to address them or answer them in your next week's update. Okay, yeah, and so I'm at a conference right now and I'm listening to presentations, and honestly, these presentations were just as interesting and well developed as the papers I'm listening to. So yeah, great job, everyone. Okay, so yeah, really can't give you all much better compliment than that. So keep up the good work. Any questions or comments before we end for today? Any questions or comments? Okay, so I think if there are no further questions or comments, I think, yeah, we can conclude. Yeah, I'll send you all the lecture information for next week's lecture shortly. Okay, so I'll hopefully in a day or two I'll have that information sent over. Right, so please, if you folks are free to drop off, I will stick around for another minute in case there is any question. Otherwise, yeah, have a good day, everyone.
Thank you, Professor.
Thank you.
Thank you, Prof.
Thanks.